Let me come to another class of transformations in phase space, and these are transformations that have a so-called generating function or generator. And these are transformations in phase space which have the following property. We consider coordinate transformations in phase space that leave the following object invariant. The integral around a closed loop in phase space of the sum over I pi dqi, they leave that invariant. So we go from original phase space coordinates, the little q's and p's, we go to new phase space coordinates, capital Q and capital P, I, and we consider only those transformations for which we have the integral around any closed loop, sum over I, little pi dqi, is equal to integral over the same loop, sum over I, capital Pi dqi. So this is, at this point, another class of transformations in phase space. What does this imply? If we have this, if we define a coordinate transformation with this property, we can write the condition in a slightly different way. We can say the integral around any closed loop, and then we take the difference, sum over I pi dqi, minus sum over I capital Pi dqi. This must be equal to 0. Just a different way of writing it. This does not imply that the integrand inside the bracket is equal to 0. It only implies that this integrand must be a total differential of some function which I call capital G. So this must be a total differential of some phase space function G. Why? Because the integral around a closed loop of a total differential always gives 0. If this must hold for arbitrary loops, this can only be the case if this difference, if the integrand is some total differential. We had a similar situation when we talked about potentials in Newtonian mechanics. When the force can be written as the gradient of a potential, then the line integral of the force going from some initial point A to a final point B is simply the difference of the two potentials. If you go around the closed loop, so you take the line integral of the force around the closed loop, the result will always be 0, because it will be the potential at the end point minus the potential of the initial point. If the end point and initial point are identical, the difference is 0. So whenever the force can be written as the gradient of a potential, then the integral of the force around a closed loop is equal to 0. That holds generally. The integral around a closed loop of a gradient is equal to 0. And this is what we have here. As long as the integrand inside the bracket, as long as that is a total differential, which translates into a gradient, then the integral around the closed loop will be 0. So we have a first consequence of our definition. If we consider coordinate transformations that leave this loop integral invariant, then it is clear that this difference here in the integrand inside this round bracket, that this must be a total differential. Now, as I said, the g can be at this point an arbitrary function on phase space. At this point, I'd like to insert yet another mathematical object that is invariant under canonical transformations. And I'd like to give the argument, a sort of a very simple argument for the one-dimensional case. And then I'll just state the result for the higher dimensional case. But this is just a simple argument for one dimension to make it plausible. And the starting point is the observation that we had made before, that canonical transformations preserve volume in phase space. When you look at phase space with coordinates q and p, and you pick out some volume here. That is, in that case, in the one-dimensional case, this is an area. It's two-dimensional. And what you can do, at least formally, you add a third dimension. And in this third dimension, or with the help of this third dimension, you can introduce a vector that is normal to that area, and you can write this area in this vector form. So you have the oriented area element and then a scalar product with a unit vector. This unit vector with component 0, 0, 1 is equal to the curl of another vector with components minus p, 0, 0. Now you can convince yourself that when you take the curl of that vector, then you get the vector with components 0, 0, 1. But when we write it in this form, as the area integral of a curl, we can apply Stokes' theorem. And we can write this instead as a line integral around the loop going around the border of the area of d pi scalar product. It's a line integral in phase space, and we have position vector in phase space, which is little pi. Scalar product with that vector minus p, 0, 0. Now the infinitesimal distance vector has components dq, dp, and then d, this third coordinate that we had introduced here, this auxiliary coordinate. But this doesn't really matter how we call it, because when we take the scalar product with the other vector, that vector has component 0 there, the third component is 0, so it doesn't really matter how we call this auxiliary axis. What remains of that scalar product is simply the loop integral of minus p dq. And so we find that since the area is conserved under a canonical transformation, and since the area can be rewritten as that loop integral over minus p dq, this implies that also the loop integral p dq is conserved. And this holds for any loop. So this is yet another consequence of the fact that the coordinate transformation is canonical, that not just the area is conserved, or the phase space volume, but as a consequence, or equivalently in one dimension, this loop integral p dq is conserved. Now this argument can be generalized. It becomes a bit more complicated. You cannot simply do it starting from a volume integral. You have to use a different starting point, but you can generalize that to higher dimensions. And the result for arbitrary dimension is that the loop integral and then sum over I pi dqi is conserved. So this is one further property, important property of canonical transformations, that they preserve this loop integral. We looked at coordinate transformations that leave this loop integral invariant. It's just the same loop integral that I just wrote on the previous page. So we know already canonical transformations have this property. What we have not shown yet, but I will argue later, that any coordinate transformation that leaves this loop integral is in fact canonical. So it's a one-to-one correspondence. Up to now, we have only shown that any canonical transformation preserves this loop integral. You see that the differential dg, that's a linear combination of d little q's and d capital Q's. This suggests that g should be considered a function of the little q's and the capital Q's. If I can write its differential as a linear combination of d little q and d capital Q, then I expect that g should be a function of the little q's and the capital Q's. And then, assuming that, you can write the differential of g simply as sum over all the partial derivatives of g with respect to the little q's times d little q, plus the sum over the partial derivatives of g with respect to the capital Q's times d capital Q. And then simply by comparing the coefficients in front of the differentials, you find that you can identify that the little pi, so the momentum component in the original coordinates, must be given by the partial derivative of g with respect to little qi. That's equation number 1 on the right-hand side. And minus capital Pi must be the partial derivative of g with respect to capital Qi, and that's equation number 2 on the right-hand side. Now look at these two equations, number 1 and number 2. The first equation, you have on the left-hand side, you have the momentum, little p, so in the original coordinates. On the right-hand side, you have something that depends on little q and capital Q, on the old and the new position coordinates. So you have little p as a function of little q and capital Q. And you can solve that equation, or let's assume that normally you can solve that equation for capital Q. And then you get capital Q as a function of little q and little p. The second equation, equation number 2, gives you, on the left-hand side, you have capital P, so the new momentum coordinate. On the right-hand side, again, you have something that depends on the old and the new position coordinates. But the new position coordinates, the capital Q's, with the help of equation number 1, we had just expressed in terms of little q and little p, in terms of the old coordinates. When we insert that in the second equation, we get capital P, so the new momentum coordinate, as a function of the old coordinates of little q and little p. So taken together, these two equations, number 1 and number 2, give us the new phase-space coordinates, capital Q and capital P, as a function of the old phase-space coordinates, little q and little p. And therefore you see that this function g actually determines completely the coordinate transformation from the old phase-space coordinates to the new phase-space coordinates. Now, if we know the g as a function of little and capital Q, if we know that function, then with the help of equations number 1 and number 2, we can specify the coordinate transformation from old to new phase-space coordinates. This is the reason why this function g is called the generating function of the phase-space coordinate transformation, because this function determines the coordinate transformation. That's why it's called the generating function. In this discussion here, we always assumed that the coordinate transformation is time independent. And that's reflected in the fact that the generating function g is also time independent. You can generalize that, you can go to time dependent phase-space coordinate transformations by making the generating function time dependent. And that's also a step that we are going to take a little bit later. At this point, I would like to show the reverse, that any coordinate transformation in phase space that leaves the loop integral invariant is in fact canonical. So the reverse direction. And again, for simplicity, I would like to give the argument only for one dimension and simply claim and encourage you to try to prove for yourself that this also holds for arbitrary dimensions. So once again, we restrict ourselves to one dimension. What we already learned is that when the loop integral is invariant, we just learned that then there exists a generating function g. And the differential of the generating function g is given by p dq in the old coordinates minus p dq in the new coordinates. Now we would like to consider the new coordinate, position coordinate q, as a function of the old phase-space coordinates. When we take the differential then of the new position coordinate dq, we get the partial with respect to little q at fixed p dq little q plus the partial with respect to original momentum dp. Inserting this into the statement on the equation on the left-hand side and grouping all the terms that have a differential dq and the terms that have a differential dp, we get this is little p minus capital P times the partial big Q, small q, dq minus capital P times the partial with respect to p at fixed q dp. Well, but what we could have done also is we could have now considered the generating function g as a function of the original phase space coordinates of little q and little p. And we could have written the differential of g, dg, in terms of d little q and d little q and d little p. And then in front of the dq we would have had the partial derivative of g with respect to little q at fixed little p. And likewise for the term in front of the dp. Now we can compare coefficients in front of the differentials and identify that this must be the partial derivative of the generating function with respect to q at fixed p. And that here, including the minus sign, that must be the partial of the generating function with respect to p at fixed q. Next, we consider a second order partial derivative of the generating function. We consider the second order partial derivative of the generating function with respect to q and p, little q and little p. The order of partial derivatives is irrelevant. So we can view this either as taking first the partial with respect to q and then with respect to p, or alternatively, we take first the partial with respect to p and then with respect to q. That must give the same result. In the first case, we can use for the partial derivative of g with respect to q, we can use the result up there that's encircled in blue. Now if we then in the next step take the partial with respect to little p, we get first the term partial of little p with respect to little p, this is equal to 1, minus, and then we have the partial of capital P with respect to little p at fixed q times the partial of capital Q with respect to little q at fixed little p. And finally, we have a contribution capital P and then the second order derivative of q with respect to little q and little p. This is the first alternative. The second we use for the partial derivative of the generating function with respect to the original momentum. We use again the result from the equation above, encircled in blue, the lower coefficient encircled in blue, and there we get first of all a partial derivative of capital P with respect to little q at fixed little p times the partial of capital Q with respect to little p at fixed little q minus p times second order partial derivative of capital Q with respect to q and p. So we have two different expressions now for the second order partial derivative of the generating function with respect to q and p. Of course, these two expressions must be equal. So we can simply equate the upper result with the lower result. We find that the last term in both results is identical. The last term where we have the second order partial derivative of capital Q with respect to little q little p and the capital P in front. So these two terms, they are identical. And what's in front, this here, this must also be equal. But when you rearrange these terms, you see you can you equate the upper expression and the lower expression, and then you take from the upper expression you take the partial derivatives on the right hand side of your equation, and then you find 1 must be equal to, and then you have partial capital P with respect to little p times partial capital Q little q minus partial capital P little q times partial capital Q little p. Do you recognize what that is? That's a Poisson bracket. Yeah? So you find this means that the Poisson bracket of capital Q and capital P evaluated in the original coordinates little q and little p, that this is equal to 1. Under this transformation, which is generated by G, the Poisson bracket is preserved, and this is the defining criterion for a canonical transformation. Now, strictly speaking, you also have to check that the Poisson bracket of Q with itself is 0 and of P with itself is 0, but this is trivial because the Poisson bracket of any function with itself is always 0. So you don't have to check that here in the one-dimensional case. In the higher dimensional case, this requires a bit more work because then you have different components for position and different components for momentum, and you have to check that all the Poisson brackets amongst themselves, that they vanish. But as I said, this gets more complicated, and I just claim that this also works for higher dimension. This is here just a simple argument for one dimension. So now we have it both ways. We know that canonical transformations preserve the loop integral, and we know that transformations that preserve the loop integral are canonical. So in other words, we can use the conservation, the invariance of the loop integral, as an alternative criterion for checking whether a transformation is canonical. Here I would like to add a little example for a canonical transformation that is generated by a generating function. It applies to the harmonic oscillator. So the harmonic oscillator has a Hamilton function which is equals the physical energy and the mechanical energy. It's kinetic energy p squared over 2m plus potential energy, which equals mass times omega squared q squared over 2. So we're doing this in one dimension again to keep things simple. And here we could pick a generating function, and you might wonder, it looks a bit unexpected, but let's choose the generating function g expressed as a function of the old and the new position coordinates. So little q and a new position coordinate capital Q. And this generating function we choose to be mass times omega over 2 times little q squared times the cotangent of capital Q, the new position coordinate. Let us see what kind of transformation in phase space coordinates that generates. And to see that, we have to use the equations for the momenta. So we have little p is the partial of the generating function with respect to a little q, which is equal to mass times omega times q times the cotangent of capital Q. And the momentum capital P, that is minus the partial of the generator with respect to capital Q. So we get 1 over sine squared capital Q. With these two equations, we can either express the new coordinates as functions of the old coordinates, or alternatively, and that's what I'm going to do here, express the old coordinates in terms of the new coordinates. Let's start with the second of these two equations. We have on the left-hand side, we have capital P, the new momentum coordinate. On the right-hand side, we have the old and the new position coordinates. And we solve that second equation for the old position coordinate. And we find that the old position coordinate equals 2 times the new momentum over mass times omega square root, and then we multiply with the sine of the new position coordinate. So that's the second equation solved for the original position coordinate. Then we use the first equation on the previous line. We have little p expressed as a function of old and new position coordinates. Now for the original position coordinate, little q, we use the result that we just obtained. Multiplying with mass times omega first gives us 2 mass times omega times capital P square root. And then we have the cotangents multiplied with the sine of q, and this is equal to the cosine of q. So here we have the transformation law, the transformation rule between the old and the new coordinates as generated by our generating function g. Now the big advantage of this approach is that by using a generating function, we know, we are assured that this transformation is canonical. Well, that's what we just showed. When we have a generating function, then the resulting coordinate transformation is canonical. So if you just looked at this transformation law, you couldn't easily see that this is a canonical transformation. But when you know that it comes from a generating function, then you are sure that this is a canonical transformation. What happens now under this canonical transformation with the equations of motion? We learned earlier that canonical transformations preserve the structure of the equation of motion. And provided the canonical transformation is time independent, they also preserve the Hamilton function. So exploiting the fact that it's canonical and time independent, we can immediately write the Hamilton function as a function of the new coordinates. This is simply the original Hamilton function which depended on little q, and we simply express the old coordinates in terms of the new coordinates. So this is the simple rule for obtaining the Hamilton function in the new coordinates. And when we do that, so we get, first we have little p squared over 2m. We insert our transformation rule for little p. then we get a 2m omega p, the 2m cancel out, so we are left with omega capital P times the cosine squared of q. The next term, we have a little q squared in the original Hamiltonian. We insert the transformation law for the coordinates, and again, amongst the prefactors, several terms cancel out, and we are left with omega p, and then we have a sine squared of q. But now this becomes extremely simple because cosine squared plus sine squared is equal to 1. So the Hamilton function in the new coordinates is simply equal to omega times p, capital P. We have an extremely simple Hamilton function. Then we can proceed to write down the Hamilton equations in the new coordinates. We know, since the transformation is canonical, they have the same structure. So again, we know that it must hold that capital P dot is minus the partial of the Hamilton function with respect to the new position coordinate. But the new Hamilton function doesn't depend on capital Q anymore. So this is equal to 0. So we immediately get the result that this new momentum coordinate is conserved, is simply a constant of the motion. And we get the other Hamilton equation is capital Q dot. This is partial of h with respect to capital P. And this is omega, because the Hamilton function is simply omega times p. Partial derivative with respect to p simply gives omega, and therefore we have q of t is equal to omega t plus some constant which we can denote by beta. So you immediately get the solution for the equations of motion, for the Hamilton equations in the new coordinates. It's extremely simple to solve the equation of motion. And then you can insert this result back into the transformation law, and you get the solution in the old coordinates. So if you look at this formula for little q, for example, that's this prefactor times the sine of capital Q. Simply insert for capital Q omega t plus beta, and you get q of t, little q of t. And in the formula for little p, you have a prefactor times the cosine of q. Simply insert for q of t omega t plus beta, and again you have the solution for p of t. So in this way, this is one way of solving the equation of motion for the harmonic oscillator. Of course, it's perhaps a bit overdone to use this whole apparatus to solve the harmonic oscillator in one dimension, because there are easier ways of solving it. But this is just to illustrate the principle, what you can do with these canonical transformations. In general, what you try to do when you have a complicated problem, you seek a clever canonical transformation that simplifies a lot the Hamilton function and the equation of motion. And then you solve it, and then you go back to the old coordinates.